Okay, good afternoon, everyone. Thanks for attending the ASA SLDS webinar. So before we start, a few housekeeping things. If you have any questions, feel free to during the talk, like you can type in the Q&A session, and or you can raise your hand, and then so that I can unmute you, and then you can communicate directly to Professor Karmakar. And we will also have like a Q&A session afterwards. So if there's some question that's non-clarification question, let's leave it till the end. And if you need to leave during the middle of the talk, that is entirely okay. So the talk will be recorded, and the recording will be posted on the ASA SLDS website, so which is here. Okay. And so our speaker today is Professor Bikram Karmakar from Department of Statistics at University of Florida. Professor Karmakar got his PhD from the Wharton School, University of Pennsylvania, and his advisor is Professor Dalen Small. Dr. Karmakar's research interests include causal inference, observational studies, application of statistics to social sciences, health sciences, public policy and marketing. He's a prolific researcher who has published 5 R packages, 2 book chapters, and more than 20 papers. Many of them are in top journals. His research is supported by National Science Foundation and multiple grants from National Institutes of Health. Okay, so without further ado, let's welcome Professor Karmakar.
Thank you, Sophia. Thank you, everyone, for coming. Thanks for Sophia for the kind introduction and also for inviting me to give this talk. And let me get started. As you can see, this talk is on causal inference. But the way this talk is structured, there are going to be like 3 parts. First part is brief, shorter. The second and third part, they are slightly longer. In the first part, we're going to do a little bit of ramp up into causal inference. We'll be discussing randomized experimentation. The second part is going to be on observational studies, and I'm guessing this is a data science audience, so I'm expecting the second part is going to be quite exciting. But the purpose for the second part is not to be comprehensive about observational studies, but to give you an idea to ramp up again to the third part, where we're going to discuss a new paradigm for causal inference in observational studies. And the third part of the talk is based on work with student Bikram Karmakar, who got his PhD this year from University of Florida, regarding statistics. So let me get started with the basics. So we are talking about cause and effect. So in causal inference, we obviously want to ask the question of the type, what is the effect of a treatment or intervention or policy. And these terms, treatment, intervention, policy, they are used interchangeably. Even in the context, they don't mean exactly what they are. So for example, if you're comparing statin and non-statin, statin and non-statin are 2 different treatments, and you might be interested in their effect on neuropathy. Whereas in other contexts, in a social science question, you'll be interested in public schooling or private schooling and their effect on educational achievement. Now, these are not technically treatments, but we're still going to call them treatments. So public schooling and private schooling are 2 different kind of treatment. We're interested in their effect. Obviously, these are important questions. The first question will indicate whether you need to be concerned about using statin, popularly used drug. Whereas in the second part, whether if you know public or public schooling, private schooling is better or not, can indicate more investment or more governmental incentive towards one of these. Now, when it comes to causal inference, you might have heard of saying something like you cannot put causality with statistics. And nowadays it is not a very popular saying, but as late as 1965, for example, Sir Austin Bradford Hill wrote that no formal tests of significance can answer those questions. At the same time, you have people like Fred Mosteller, who said you can only put causality with statistics. So I'll ask you to remember this year 1965 for a while, because I'm going to revisit this year in the context of observational studies. where we'll see that our observational study grew parallelly with this concern about statistics and causality. But when Professor Mosler was talking about you can only prove causality with statistics, he was really talking about a very particular kind of statistics. A statistic that can technically or at least philosophically can prove causality. And he was talking about randomized experimentation. Conceptually, randomized experimentation is not too difficult. You can think of a group of people, like in a clinical trial, you have a treatment or a placebo, you have multiple treatment, whatever it is, and you have a procedure to randomly assign a group of them to one treatment, another group to another treatment. Even the conceptually simple, actually conducting a good randomized experiment is pretty heavy-handed. In the back end, you have to think about a very well-organized protocol, even before doing experimentation, which might include who can or cannot join the experiment, how many study participants, the sample size will be needed, a description of the intervention or the treatment that might be given. And obviously, when I'm listing them, I'm thinking of experimentation involving individuals or maybe animals and treatment, but you can map these same context in same things in the other contexts. Protocol might also include or probably should include what researchers want to learn, what they want to measure, how they want to analyze the data, and also should include if the study results are published, who should be the contact person to validate or check anything that might be of concern to the reader. And all of these are sort of required, for example, if you are doing an FDA drug approval application. Also, top journals such as New England Journal of Medicine, they publish protocols, and also you can register clinical protocols in clinicaltrials.com. So, with this setup of randomized experimentation, the next part of randomized experimentation is obviously randomization. To quote John Tukey, who says that our best watchwords are often these: randomize, randomize. And the second randomize is in caps. This is John Tukey on the right. I can't imagine he's yelling randomize. I am probably guessing just going to emphasize that you should randomize, right? So randomize is a very big deal in randomized experimentation, at least from both practical and statistical point of view. From practical point of view, it's important because it gives assurance of impartiality of treatment assignment. And it also gives you it also provides a convenient means of implementing the treatment. So these are practical things. But at the same time, the third point that I have noted here is both practical and also technical. It creates like-to-like comparison between treatment. So in technical words, any pre-treatment covariate will have the same on an average properties, means, variances, distribution across treatment groups. Right? So these pre-treatment covariates need not be measured. Even for unmeasured covariates, a randomization and good randomization or a honest randomization will give you like-to-like comparison. Now, from the statistical point of view, the key part of randomization is what R.A. Fisher said is the reasoned basis for inference. So you don't need any other distribution assumption for your inference, except for the fact that a physical randomization took place where individuals were assigned to treatment or control. So when Fisher argued about this reasoned basis for inference, he said, I simply cannot make head or tail of what the man is doing. Whereas at the same time, Jerry Newman thinks to say that it's a very brilliant idea. So we'll revisit a little bit of how randomization can be used for inference, but let's think about this. If we can solve, Fred Mosteller is saying that you can solve or answer causality with statistics using randomized experimentation, why just don't we do randomized experimentation whenever we are interested in it? And obviously, the big reason is there are hindrances, right? So you cannot, in good conscience, restrain treatment which might be beneficial from treatment. Or you cannot just give people treatment which might be harmful. So in all of these cases, for ethical reasons, you cannot do randomized experimentation. There could be other reasons, there could be practical reasons that you cannot do randomization. So even though it is the gold standard, even though this is what we want to achieve, for reasons we cannot do it, and that what takes us to observational studies. Now we are in an era, or we have been for quite a while in the era of data science, which means we have a bunch of data from different sources, we can process them, we can analyze them, and that has propelled us to use non-experimental data for causal inference. And that is the purpose of observational studies. So this is the second reference. This is a quote by Bikram Karmakar, who first discusses or formalizes the idea of an observational study in the following quote. It says that an observational study is an empirical investigation in which the objective is to elucidate causal relationships in which you cannot do controlled experimentation, in the sense of being able to impose procedure or treatments in a random manner, right? So you take a randomization, but you still want to do causal effect interpretation. Now, remember 1965, so it's been what? 60 years? That's been quite a while. So if people have been working on, or people already were working on observational study and statistical tools to solve causal inference in observational studies, why do we need to, why are we still doing it? People must have figured out how to do it. Unfortunately, things are pretty complicated. So if you think about observational studies, there are very big notable failures. For example, these ones, hormone replacement and heart disease, vitamin supplemental mortality, all of this context, there have been multiple observational studies, all of them indicated that they have health benefits, which sort of motivated randomized experimentation, and in that cases, the randomized experimentation showed that the observational study results were not correct. So these are failures of observational studies, and we need to be conscious about these failures. And what should be our goal is the following. We should be conscious about not making too many mistakes or trying to avoid as much mistake as possible when we make claims of causality using non-randomized studies, such as observational studies. Right? So that motivates the rest of the talk. So when we figure out what people have proposed to avoid these mistakes and discuss a little bit of all of them. We won't be able to discuss many of them. There are obviously long literatures. And then we'll come back to our proposal that can be in some way solve this problem of mistaken causal inferences from observational studies. Now, what is the problem? What is the basic problem in the observational study? Obviously, we're not going to do randomization. One or two approach in observational study is to try to mimic the standard practice without doing the randomization. Obviously, we don't have a very strong protocol. So, for example, we also cannot do physical randomization. We cannot do blind studies or double-blind studies, stuff like that. You cannot do a lot, but you can try to do some. So you can maybe slightly mimic randomization, but the problem is the treatment and the control group may differ in ways other than the treatment that controls out. Right? How can they differ? They can differ in obvious ways. They can differ in ways that are observable, measurable, right? In that case, there are statistical methods to control them. You have stratification, matching, or you can have regression adjustment. And if you're not familiar with these terms, I'll show you some examples of both matching and also regression adjustment to address overt bias or just major differences in observational study. But there's always a possibility that the major differences are not enough. There are unmeasured differences that makes the treatment and the control different. And because of these differences, your inference, your causal inference is never going to be true. You will always be a constant that the causal effect or the stated causal effect can be explained by other things, other differences. So how have people addressed this hidden bias earlier? There have been, it is a continuous process that there is this passive concern about bias. So most studies, or almost all studies, they will discuss this possibility of hidden bias in their discussion section. And this is quote unquote ineffective because there is no quantification of hidden bias, maybe deduction sometimes that if this unmeasured confounding is possible, our study effect will show a negative or a positive bias, but never a complete solution. But it's still effective to know that what authors have thought about as unmeasured confounding. It's valuable, but not very effective. There are some active and effective ways to address this bias. Some of them are listed here. For example, sensitivity analysis, two unmeasured confounding, tests for hidden bias, also replicating the effect without the bias, and eliminating sources of bias as explanation for association between treatment and control. Now, you can read a lot about all of these things, and there is a lot to talk about. What I'm going to do is I'm going to go into a little bit of detail in sensitivity analysis, but I'll have a chance to also discuss with you randomization as a basis for inference. And I'll hint at the test for hidden bias and evidence factors, which is replicating treatment effect without bias. Okay. So let's start with a study. A study of smoking and lung cancer. This is a well-regarded study of causal inference. People by now are assured that smoking causes lung cancer. But let's look at this study by Hammond, 1964, around the same time as Bikram, who was also part of this kind of studies. Right? So Hammond used 36,975 heavy smokers and non-smokers, and you have all of these pre-treatment surveys that are measured. You can imagine usually older individuals are smokers compared to younger individuals, at least in today's age, and there are differences in smokers and non-smokers in all of these surveys. So it makes sense to adjust for them. And one way to adjust for them is matching. So what do I mean by matching? Look at all of these non-smokers, match a smoker with a non-smoker as closely as possible in all of these co-values. Now, there are matching algorithms. There are ways to match them as closely as possible. There are ways to refine the match, find exact match, find near exact match, to find balance. There is a lot of literature on matching. But let's suppose that we have done this matching. So we have a bunch of pairs. In each pair, we have a smoker and a non-smoker. We can tabulate the result. We can look at them and look at their 3-year follow-up of whether they have lung cancer or not lung cancer. So what is this table showing? This table showing, for example, 0 people, or if there are 0 pair where both non-smoker and the smoker in the pair had a lung. There are 110 pairs where the non-smoker did not have lung cancer, but the smoker had lung cancer. There are 12 pairs where the non-smoker had lung cancer, but the smoker did not have lung cancer. And there are these 36,853 pairs where neither smoker or non-smoker. So what do we want to ask? We want to ask if there is an effect of smoking on lung cancer. So let's look at a statistic. Let's look at the number of discounted match pairs in which the person with lung cancer smoked. So in our observed data, this number is 110. So we have in total 122 discordant pairs where one had lung cancer, the other did not. And among them, the 110 of these had smoker having lung cancer, but the non-smoker did. Okay, let's ask this question. If there was no association, there was no association of smoking and lung cancer, what is the possibility that we're going to see this number 110? Right? That is your basic question of statistics. That is the basic way you calculate p-value. So condition on the fact that we have matched pairs where one of them smoked, the other one did not smoke. So we have this 122 pairs if smoking and non-smoking was equally likely, you will expect that half of them will have non-smoker having lung cancer, half of them will have smoker having lung cancer. So roughly, this number on average should be 52. But what is the distribution of that number? You can get that distribution and you can plot. How do you get that? That's why you use randomization, right? So you randomly assign in each of these discordant pairs, one of them to be treated with smoking, one of them to be not treated with non-smoking. Each time, you calculate the test statistic value with this number of discordant pairs, where you have assigned the smoker to have lung cancer. Enumerate all of these numbers, draw them. That gives you the distribution of the test statistic, right? And that's the distribution that's plotted here. And as we expect, the 62 or 16 is the expected number, the median. The number that we saw in the data, 110, is way far to the right. It gives you an idea, the effect is very strong. The p-value is very small, right? Is that enough of evidence showing that smoking causes lung cancer? It would be if the randomization was actually a true randomization. But here, the randomization is a pretend randomization. It only controls for the covariate that we have adjusted for. Now, a significant covariate that was pointed out by Fisher, was that gene could cause both smoking and lung cancer. And is this a passive or ineffective way of arguing against treatment effect? Well, Fisher actually did more than just argue that gene can cause smoking and lung cancer. He collected data showing that there is strong association between smoking and gene, right? So in this paper from 1958, this is actually a note from 1958, he showed that in hospital data, there is strong evidence of considerable influence of smoking on smoking by genotype. Right? Now the question is, if there is still possibility that gene type can affect smoking, the result that we got from previous exercise, but the people who was very small, the number of 110 was very far from our expected distribution. Can gene really invalidate our result that smoking can cause lung cancer? Now, this is a scientific way of arguing against possibility of unmeasured confounding. We did not have data on gene, but we can do is we can consider a sensitivity analysis. A sensitivity analysis answers the following type of question. It says, if there is possibility of unmeasured confounding, how strong that confounding need to be to invalidate our result that adjust only for the observed covariates, right? So let's look at our exercise again. We have this test statistic T, where T is the number of discordant matched pair in which the person with lung cancer is small. Right? Remember, we had 122 discordant matched pairs. So the probability that T is greater than 110 is the sum of A1 into A22, and you have this Bernoulli probability, P1 to the AI, 1 minus P1 to the 1 minus AI, where P1 is the probability of the fact that the lung cancer, probability that the person with lung cancer is small. Now, if the matching was enough, then P1 will be half, and that's the exercise that we did before, right? But if there is another confounding, it is possible that the person with lung cancer smoke with a higher probability because of this association between another confounding, for example, gene with smoking and lung cancer. That increases the probability that the person in the matched pair who had lung cancer will smoke. So let's define a parameter gamma, a sensitivity parameter, which says that among two people with the same measured covariates, the maximum odds ratio that one person will receive treatment rather than the other is the odds ratio is gamma. So, in other words, If gamma is 1, then both of them will have equal odds after matching for the observed probability. If gamma is 1.5, then the unmeasured confounding could increase the odds of person receiving the treatment by 50%. If gamma is 2, then unmeasured confounding can double the odds of 1%. So gamma, the worst possible value is 1. The further gamma is, the further or the more influence we are allowing of unmeasured confounding on our study. And this is a little bit of a technical exercise, but if you define P plus, which is gamma over 1 plus gamma, and you can check that if gamma equal to 1, this comes out to be half, right? 1 over 1 plus 1 is half. Then the maximum possible P value is less than equal to this sum, where P1 is replaced by P plus. This is a convenient formula to calculate the largest possible P value when you allow for gamma and amount of unmeasured constant, right? So we can calculate this for different values of gamma. Let's do that. Let's say I take gamma including from 1, 2, 3, 4, 5, 6, and so on. The table here shows, based on that study by Hammond, up to gamma value of 5, we have the maximum P value less than 0.05. In other words, an unmeasured confounding that could increase the odds 5 times will still be insufficient to explain away the fact that smoking can cause cancer. Whereas, if the unmeasured confounding is strong enough that it increases the odds of smoking person having lung cancer, then it would be invalidated. Compare that, for example, to the other outcome, which is sclerosis of the liver. In this case, at gamma equal to 1, we do have a significant P value. P value is less than 0.0001. Whereas if you allow some amount of little amount of unmeasured confounding 1.5, that effect is there. So it's highly sensitive to possibility of unmeasured confounding, whereas lung cancer is not. Okay. So this gives you a sort of assurance about your inference. So it gives you a robustness to the possibility of unmeasured confounding. Sensitivity analysis can buy you a lot, right? But there are limitations. So what are the limitations? First, this value of gamma, this is something we are tuning. This is a parameter that we are playing around with. We know that gamma is 1, is the smallest possible. We know how to interpret gamma, but we do not know what value of gamma is sufficient. So studies can be insensitive to moderate bias, but be wrong because of the fact that there is large bias. For a given value of sensitivity parameter gamma, we can get estimates and confidence interval by inverting the test. I reported P values to you, but you could as well get confidence interval and interval for estimates. But the fact that because gamma is allowing you to relax the possibility of unmeasured confounding, by the amount you relax, you can only get an interval estimate of your treatment effect other than a point estimate. And the larger you take the value of gamma, the larger the bound goes. If you take gamma very large, it will be very large interval. So any amount of effect, however large, is always explainable by certain amount of unmeasured confounding. Right? So at some point you have to give up, unless you know someone else to address this particular gamma. Of course, there have been studies to understand what is the role of gamma. How can we understand if this gamma is sufficient or not? But we're not going to go into that. So that is sensitivity analysis. The second way of addressing possibility of bias is test for hidden bias. Right? So it would be useful to have a test for large or moderate amounts of hidden bias. And there have been significant work in this area, for example, using negative control. So what does the negative control do? So it asks the question, is there an outcome which the treatment does not occur? And if the confounding pattern between that negative outcome, the negative control outcome, and the outcome we are interested in one way, we know that the outcome, the negative control outcome did not have an effect. In the other way, the outcome we are interested in investigating. So from one to another, you can sort of transfer the information and that will give you a test for written bias. I'm not going to go into the technical details here, but I'm just indicating to you that there is this way of addressing the problem. But you need to remember that you need this extra information, you need this extra structure to your study, which is a negative control. And finally, you can also do a replication of an observation. Now, replication is not repetition. It's not like I do the study, 5 days later, one of my colleagues does the same study within the same data, or replicate a copy of the data. When we talk about replication of an observational study, we talk about replicating the effect without replicating the bias. Right? So consider this example. Again, sticking to smoking, we are asking, as cigarette smoking increase, homocysteine level in the blood. Now you can compare people who smoke a lot and then people who don't smoke, just the way we did before, by matching. But you can also think about the following. When smoking or people smoke, it gets internalized as cotinine. Right? So cotinine works as a biomarker for smoking. So when you compare people with high and low cotinine, in their terms of their homocysteine level, that gives you another replication of an observational study. Asking similar question, does smoking increase homocysteine level? But there could still be bias when you do this other comparison between cotinine and homocysteine level. Because there could be physiological processes that confound them. But this physiological confounding is not same as what we have confounded smoking and homocysteine level. So that's one way to do application of the observational study. Now, evidence factor is a technical tool to do this formally in an observational study, and it can buy you a lot. The key features are the following. It gives you multiple comparisons where the biases are non-overlapping, just the way we discussed before, but also it gives you statistically independent or near independent tests, which is important because it can distinguish new evidence from previous evidence. So the evidence is not repeated. If two tests are highly dependent on each other, if one of them is significant, possibility is other one is not significant. We don't want that. We want them to be separately significant or insignificant. So what we're really trying to do is we're trying to avoid this misunderstanding, which has been talked about by Wittgenstein, who says, okay, several copies of the morning newspaper cannot assure you of the statement to be true, right? You need defined perspectives. You need independent evidence. Okay. And now that is sort of a wrap on the second part of our talk on observational study, the state of the art. Not a complete or comprehensive discussion, but important enough to propel us toward the third part, where we're going to discuss about our contribution towards this area. So let us start with some notation. We're not going to be a math heavy, but some notation will be useful. So let's say we have a binary treatment. So Zi is a binary treatment indicator. Zi equal to 1 is treated. Zi equal to 0 is not treated. Xi, treatment covariates or characteristics of individual I. You have potential outcomes, potential outcome yi1 and yi0. These are the two possible outcomes of unit I if unit was treated versus not. So at one point of time, depending on what the unit I gets, you can Zi with yi and xi, where yi is equal to Zi times yi1 plus 1 minus Zi times yi0. So that's the mathematical way that the operation outcomes are connected to with the observed outcome. Okay. And you can see that because you only see yi, you do not see both yi1 and yi2. Whereas these potential outcomes or their differences, something like yi1 minus yi2, that is an indication of individual i's treatment effect. In particular, in this work, we'll be interested in the conditional average treatment effect on the treated. In short, CATT. What is that? This is extended value of yi minus y0, condition on treated, and the characteristic of the individual mu x. Right? Now, there are different estimates. The one where in this, obviously, for smoking example, this is particularly in school one, you cannot imagine everyone to be smoking. You only want to understand what is the effect of smoking for the smokers. Right there. Now, if over bias, if measured confounders or measured covariates was sufficient, then we could estimate the scat average treated just by the following component. So what is this doing? It's saying that take for each individual or each strata X, take the average outcome for the treated minus the average of the control, right? And average over X. So if you don't average over X, you get beta of X, and beta of X is an identification of your tau of X. So going forward, I want you to remember two notation, particularly tau of X is our parameter of interest, is our estimate of interest. We don't know tau of X. We want to estimate it or we want to infer about it. Beta of X, we can estimate because beta of X is this difference of two averages based on our observed data y, x, and z. So we can estimate it. Tau of X, we are interested in, we cannot estimate it, beta of X can estimate. Now, this assumption of no unmeasured confounders, which in technical terms says the potential outcomes are independent of the treatment given the characteristics that we have observed, says that beta of X is equal to tau. If you don't have this assumption, then it is not true. And if it is not true, the question for us is what can we do? We're not going to assume identical structure. We're not going to assume that we have a negative control. We're not going to allow us to do sensitivity analysis because sensitivity analysis will eventually fail after a certain level of gamma. We don't have clever ways to do evidence factors. What can we do? To motivate our method, we're going to do the following example. So let's look at it. This is a similar example where let's look at this plot. We have 10 groups, split it into 5s, 5 on the left, 5 on the right. In each group, we have some who are treated, we have some who are not treated. So black points are treated, gray points are not treated. On the right and on the left, there is no treatment effect. So the individuals will not experience any effect of the treatment regardless of which treatment they receive. But on the left, the treatment is biased. So people with higher outcomes are more likely to get the treatment. People with lower outcome are less likely to get the treatment. On the right, it does not matter. Both people, regardless of the outcome, people are equally likely to get treatment or treatment or control. Okay, so some difference are clear. Obviously, you see more black points on the top and more gray points in the bottom on the biased cases. Whereas in the unbiased cases, the black and gray points are roughly on the same place. But I also want you to note the other thing. Look at the variances of the black points on the left and variance of the black points to the right. It does appear, if you really notice, that the variances of the black points to the right are larger compared to the variances of the black points to the left. Same. The variance of the gray points of the right are larger than the variance of the gray points of the right, to the left, on my bad. So this difference in the variances does show up when you compare bias versus unbiased treatment assessment. Right? So if we somehow can compare these variances, we can identify the bias. Right? The text here says exactly what I told you. Okay, so what we want is an idea of how to get the variances in the right. And we can do that. Is there a way to mathematically find the bias that exists in the left? Of course, things are more complicated. Here, we could have more treatments. Sorry, we could have more covariates. We could have a treatment effect, whereas in this picture, there is no treatment effect, and so on. So what do we want? We want an estimate of the variance to the right. We're going to use this notion of resistant population. And resistant population variance is what is going to be used.
Hi, Bikram, sorry to interrupt. There is a question. Yes.
Okay.
Do you mind to address that?
Sure, I can do that.
Yeah, thank you.
Yeah.
Dr. Shen, I had just unmuted you. Feel free to ask questions. Dr. Shen? Okay, so if we okay, let's continue. Bikram, sorry.
Okay, no worries. Yeah, maybe if there is any confusion, let me pause here for a moment just to argue what I'm trying to say. What I'm trying to say is that if there is no treatment effect, just by looking at the picture, I see notable differences between the variances in the cases where there is a randomized treatment to the cases where there is not a randomized treatment. So my idea is to look at these differences in the variances to identify or probably also estimate this bias in treatment assessment. And can we do that in a mathematically concrete sense? So that's why we need this new proposal of resistant population. The resistant population variance is the variance to the right of those groups. So what is the resistant population? A resistant population is a population that was not exposed to the treatment. Okay. So for example, consider the case where we're going to study the effect of get out the vote campaign in February election on voter turnout. Okay. Campaigns are often targeted, so there is possibility of confounding. If where voter turnout is low, there might be bias, and there might be a more enforcement to do a bit of the vote campaign. So what is the resistant population? Resistant population in this case can be district level voter turnout data from previous election when there was no such a campaign. Right? So because there was no campaign, we do not have an exposure to that treatment. So that data might be used to get an estimate of the variance of voter turnout. Consider a next example where the effect of coal mining, surface coal mining on birth rate is of interest. This is an example that we will revisit in our final study. Here, we could use birth rate data from regions outside of the Appalachian counties, which is a county that we'll be interested in. Because mining was not allowed in those counties, we could use the birth rate data from those counties, and that will consist our resistant population. Right? So again, what is the resistant population? It's a population that did not have any chance to be exposed to the treatment. Maybe because of temporal cases In the first case, it's a temporal case because of special cases. In the second case, special case, there is only particular area which is allowed to do subtracting, the other areas of not. Use that data to get an estimate of the variance. Okay, that's the conceptual thing. Let's get to the technical thing. How do we use this information to estimate our effect? Okay, that's our estimation variance. Variance y is 0, even x equal to x. Now, the theory stated informally here says that tau x, remember, that's our CATT, that's our estimate of interest. Beta x, remember, that's the same thing we want. We can calculate beta x is the difference of two means based on the characteristic. The bias between these two, which is the bias in estimating tau x by beta x, can be written out in the following form. The bias squared is equal to beta x squared minus difference of the variances in top and the bottom, the variance of treatment assignment. Okay. So everything to the right can be calculated from our observed data. Beta x is calculable. These things are calculable. Sigma square 0 is something we can calculate. And again, this is something we can calculate. This gives you an identification of squared bias of estimation. Remember here, I did not need to assume anything about the confounding. There could be unmeasured confounding at any level. There could not be any unmeasured confounding. So it is possible that there is no unmeasured confounding. And if there is no unmeasured confounding, this thing will turn out to be 0. There is no bias. Mathematically, this will turn out to be 0. If there is unmeasured confounding, this is going to give you the squared bias. Okay. So we can use that. Now we have something to put numbers in. Let's look at a special case just to get our head around it. This special case, suppose we don't have any covariates. We have a constant treatment effect. So which means we have tau is equal to tau, we have beta is equal to beta. Okay. Tau is some number, beta is some number, there is no x to talk about, so it's just the constant tau. Now, in classical statistics, in Stat 101, we know that beta is estimated by the average outcome of treated minus average outcome of the control. And the standard error is the square root of st square over nt plus sc square over st is obviously the sample standard deviation for the treated group outcome over nt is the sample size for the group. Similarly, sc and nc. So this is a very classical formula. You can use this estimate and the standard error to do t statistic if your sample is large enough, or this statistic and so on. If there is bias, beta is not same as tau. So what is the difference between beta and tau? The theory says that the bias squared is equal to the following. It's sigma 0 squared. Remember, sigma 0 squared is our resistant population variance. It's the variance on a population that was not exposed to the treatment, that did not have any chance to get exposed to the treatment. So that variance minus an weighted average of the variance of the treated outcome and the variance of the control group outcome. Okay. Over just P1 minus P. P here is obviously the average number of people getting the treatment. Right? So you see the difference of the variances, like the picture that indicated earlier, the difference of the variances gives you the bias information. Now, in classical statistics, I can estimate the bias by taking the square root of this thing, and I can estimate this guy, P sigma d square plus 1 minus P sigma d square, by your usual S full square from Stat 1. And if you remember, we also know that the difference of the averages is asymptotically independent of S full square. Okay. So S full square and this guy are independent. So what we see is that not only because of this concern about unmeasured confounding, we add a bias to it, we also increase the variance. because if you look at the variance of beta hat plus bias hat, that will be increased by the variance of this difference plus the variance of this difference, and the covariance is aspirationally 0. So there is a cost. Cost is that you pay a bias or you get a bias, but it also increases your variance, which makes sense. But also notice the fact that I have this absolute thing around bias. We can only calculate the bias squared. We cannot know the direction of the bias. That's because of this identification issue. So what we have is a 2-point identification. We can get beta x minus absolute value of bias or beta x plus absolute value of bias. We do not know which one is correct, but we know that tau x must be one of these. It must be beta x minus or beta x plus. Look at the difference between this, which is not a point estimate for sure, but it is one of these two. Compare this to sensitivity analysis, where you don't get two values, but you get an interval of values. And if you take a limit, you will still get an interval. Here, you are always assured one of these two are correct. Now, a picture or some simulation study might be useful to explain this further. Let's look at a simulation example. And I'm trying to go a little slow over here, just so we get it. So what I have done is I have considered one covariate x, which is from -2 to 2. So this is -2 to 2 is your covariate. On the y-axis, I plotted treatment effect, and this is a quadratic form. You can see. In all of 4 cases, we have the same simulation model, right? Different methods, same model. We have quadratic effect in all of them. We have defined ways of explaining the treatment effect. Now there is bias. There is another confounding which gets larger for larger values of x. And because of this another confounding, you see that the state of the world, state of the art methods like causal forest, variance causal forest, and learner, they're all estimating something, but they are biased because they're assuming that they're only getting at beta hat x, they're not getting at tau x. Why let's look at the proposed method. Picture is clearly messier. Variance is larger, as I have explained, that it adds to the variance. But it also gives you 2 sets of intervals, right? One is in darker color, one is in lighter color. The darker color one is corresponding to the positive bias case, or sorry, beta x plus bias, and the negative one or the lower one is beta x minus absolute bias. What we are assured is not that both of them will capture it. We are assured that one of them will for sure capture it. So the difference between this picture over here and other picture is that we know as sample size increases, these intervals will collapse into 2 lines, and one of those lines will be our true line. Okay? So asymptotically, larger and larger sample size in causal forest and learner, we're always going to be biased. In a proposed method, we're going to overlap with the true effect, but only one of them, the other one will be missing. If there is no other confounding, these pictures will overlap with each other. And all of these pictures will likely look the same, and all of them will be consistent for the true effect. So that's the method that we're proposing for 2-point identification and inference. Now, we have dug more deep into it, how to make an estimation, how to make large sample inferences. So I'll try to go over them quickly enough. If you have questions, I can go over them in more detail later. Okay.
Bikram, there's a question from, sorry, there's a question from the audience.
Okay, I can take it.
Yeah. Would estimating the sign of the bias require identification of the correlation between potential outcomes?
Well, actually, it will require identification of the biased direction, will require understanding the direction of the effect of unmeasured confounding on the potential outcomes and the effect of unmeasured confounding on the treatment assignment, right? So if you know the direction of how, in which direction. So for example, in the previous cases, I had a positive association between another confounder and X, and also the treatment was more likely to be given to larger X values. And the potential outcomes was more likely to be larger for larger X's. So all of these led to the case that the treatment assignment or the unmeasured confounding will increase the effect. So not just the correlation between the potential outcomes, but the correlation between the unmeasured confounding and the potential outcomes and the confounding and treatment assignment will be needed. And often it happens that, like we said, in studies, we do argue that there is a possibility of unmeasured confounding, right? So that was our passive way of addressing the bias in observational studies. So in those discussions, people do discuss what will be the direction of bias expected in the study that we are missing. So if that discussion is convenient, that discussion is in depth, you can use the discussion to understand which way is the bias possible. Then you can really know which of these two intervals you should use. Okay? So it is beyond just technical terms, it is more of scientific understanding, field understanding, and practice that can give you an understanding of which of these is the right one. Thanks for the nice question.
Thank you.
Okay. So Sophia, how much time do I have?
I think we'll have 5-6 minutes.
Okay, great. So let me briefly go over the estimation method that we are using here. So we're estimating the treatment assignment mechanism, the probability of Z equal to 1 given X equal to X, using a machine learning method. You can use anything you want, really. Anything consistent, really. We can estimate the sigma 0 square X, which is the exponential variance, by local linear regression. Similarly, we can estimate the variance of YI given X equal to X by local linear regression. The one thing that we need to be a little careful about is the fact that your bias squared, whatever this thing is, we have this quantity for bias squared. It is a mathematical expression, but that mathematical expression should be estimated to be non-negative, right? So square of something cannot be negative. So when we estimate beta X, we put a constraint on the fact that beta X should be such that our bias squared is non-negative. And you can do that with a non-convex optimization formulation of estimating beta X. You can do that by, for example, mathematical solvers like Kurobi. The one we're using is Kurobi. Okay, then. So I'm going to skip this one. That was the last slide was on estimating sigma 0 squared, and not too much discussion about that. But large sample inferences, we can consider two cases. One case, for delta X, delta here indicating in shorthand the bias is 0. Delta X equal to 0, it's also saying that there is no unmeasured confounding. In that case, we know that bias in fact is 0, but we're estimating it. So there is possibility that there is going to be non-negative random sometime. So if your H is the bandwidth of your local linear regression, after some scaling, the bias squared will go to 0 with probability half, and it will be a folded normal with probability. Okay. When delta X is non-zero, you have a bivariate normal distribution for both beta X hat, and bias squared. Don't need to take away too much information from here, only need to consider the fact that when there is unmeasured confounding, the unmeasured confounding will lead to different distributions in our estimation. we want to know, in fact, whether there is a confounding or not. So we need to be careful when we actually do inference. So what we can do is consider testing whether bias hat is large enough or not. If it is large enough, then we pretend that we're going to use the second one. So it's the second distribution. If it is not large enough, then we're going to use the first one. So when beta hat square is large, then we can use case 2 to get an asymmetric distribution. We have a bivariate distribution of beta hat and bias. So we can use that to get, using delta method, get an asymmetric confidence interval for this. If this is not large enough, then you can rely on any of the standard methods, IPW regression, AIPW. There are a bunch of methods to get confidence interval for beta x when there is no bias. So this is just this classical way or the state of the art way of doing inference for causal effect using non-measured confounders. All right, so the theory will say that this gives you a asymptotically correct coverage of tau. Okay. Okay then. So let me end with this study. It's the study of surface mining on birth weight. Surface mining is a practice of mining by blowing up mountain tops. It is often just on your backyard, right? So mostly in the Appalachian region, there are places, counties where there is permission to do surface mining. And when you blow up this mountain, there is a lot of dirt that blows in the air that can have health effect. And particular kind of health effect that we are interested in is birth weight of Indian water. We're going to use data from 4 states in the Appalachian regions. So there are 91 central Appalachian counties where it is allowed to do surface mining. 23 of those saw sufficient surface mining over the last 2 decades or 4 decades or so. So our outcome will be birth weight of newborns in 2010. Right. So our treatment group will be births in the counties in these 23 counties which saw sufficient surface mining, and our controls people will be births in the other counties which did not see surface mining. Okay. Now for the resistant population, we're going to use births in the remaining 298 counties in the 4 states that we're interested in. These states, unlike the 91 states or 91 counties that has surface mining permissions, did not have surface mining permissions. So they could not have been exposed, did not have a chance to be exposed to the treatment. Okay, as I said, the outcome is birth weight in grams in 2010. So birth weights in terms of the covariates, it will be affected by the biological factors, and we'll be using mother's age, number of prenatal visits, and number of prenatal cares, the number of months of prenatal care. That will be our covariates. We use this covariate, and to enforce that we have a good race population, we also do a matching. Remember, a population is a population which is similar to the study population. We have a matching of the 91 counties that are in our study to the 298 counties that did not have permission to do surface mining. After matching, the covariates look similar to each other. So we can use this matched groups or matched counties to estimate our sigma square estimate population variance. Here is the outcome. Here is our final slide for the study. We have 2 sets of lines. We have 3 pictures. Each picture corresponds to one of the covariates, mother's age, number of prenatal visits, number of months of prenatal care. On the y-axis, we're estimating the average effect on birth weight. The horizontal black line is 0. The dotted line is the estimate assuming there is no fit, there is no another confounding. So in most cases, this is either 0 or slightly above 0. Now, because this is slightly above 0 or 0, if you assume that the treatment effect or the bias is actually positive, bias is actually on the top side, then adding to this will actually increase the effect, right? So you'll say that surface binding actually increase birth rate. In all of these cases, which is inconvenient, which is not scientific, you cannot argue that surface binding actually had a positive effect on birth rate, it had more healthier babies. Rather, if we look at the other one, which is negative beta x minus bias, then we have the picture which is in black, right? That is our estimated effect of surface binding on birth rate. It is negative, constantly negative in most cases. It doesn't seem like mother's age has a lot of effect or a lot of modification on the effect. Similarly, prenatal visit doesn't seem like a big effect modifier, but number of months of prenatal visit does have a larger effect. People who did not have too many prenatal months of prenatal care had a poorer effect than the other people. Okay, so with that, let me go to my summary slide. The proposed method gives two possible estimates of the treatment effect, but fails to provide further information regarding which choice is right. In fortunate situation, when there is no bias in treatment assessment, these two estimates will collapse into a single estimate and will be a consistent estimate. In other situations, additional knowledge, scientific knowledge, field knowledge, or other studies can determine the right choice, can determine the direction of the bias. Okay, so here is the reference to the talk. The paper for the last part of this talk is available on archive. This is the link. Thank you everyone for listening.
Thank you very much, Bikram. Let's move to the Q&A session.